Hi everyone, welcome back. Today we want to continue our discussion on network security, and we'll also talk a little bit about cross-site request forgery. That will be our next programming assignment and also our final one of this course. Recap, last time we talked about firewalls, state versus stateless, firewalls, intrusion detection, prevention system, anomaly detection, and we talked about different layers of network protocol can be made secure. IP layer can be having IPsec to ensure authenticity and integrity. Name servers, domain name service can be running DNSSEC to ensure that you're getting the responses from the correct authoritative domain name server. And mostly it's authentication, you're talking to the right server, and then integrity, the information you get is not tampered with. And so just very quickly about DNSSEC, a little bit of recap, and it's, if you understand the TLS, and then the basic concept of how to achieve CIA, this shouldn't be a surprise to you, okay? There's small differences in terms of where to get certificate, where to get keys. But essentially, you generate keys, and this is a name server, generates a pair of keys and assign DNS records to say, this translation between IP and domain name should be like this, and I put my stamp of approval on it. It's my digital signature, and then so the translation and the signature both get sent out to the client, which the client then verify the signature. And then of course, it's always a question, where do you store the keys? So who verify the keys? And in this case, you have the parent zone endorse the child zone, and the grandparents zone endorse the parent zone. And so you can have some sort of CA like hierarchy. And then of course the root, you get the root root zone gets signed with the CA. And then in terms of where to store the public key, because this is not like web server, we go back and forth, and DNS, and it's on UDP, very simple, and so you just store the record on your name servers, and as if it is one of the translation record, and so DNS is, last time we said, it's like a database. So it's pretty practical. And last time we talked about the deployment. If you have incentive, then a lot of countries actually deployed it with very high percentage. So today we want to begin by talking a little bit about email security, and I thought, boy, didn't I have the perfect example for you guys? Last week, I served as the officer at the ACM, Association of Computing Machinery and this like society. Ninghui is the chair. We are in this security society special interest group SIG. And so last week I got this email. And then so I was reading from the top, and so it's all making sense. And I am the secretary and treasurer of SIG-SAG, so I'm expecting this kind of question in the transaction summary. But then later on, I find out, initiate a bank transfer or PayPal today. And I know that in ACM has a special, they just don't use PayPal, okay? They have special official mechanism. And this is the real email Ninghui sent to me, and you can tell the difference. Of course, the email address, he's from Purdue. And this is I realized, after I saw PayPal, I realized this is phishing. But it's just, they know the fisher know that I'm in this organization, and so there's quite a bit of insider knowledge. And of course, anyone can spoof email, and then that one phishing email wasn't really well planned. Part of the reason I think that person is expecting my reply. So that person needs to receive my response and therefore cannot use the actual person's email, the real email, right? Then my email will be sent to purdue.edu. But then of course that giveaway, you can use if you have the link, the phishing email, phishing link embedded, then you can just spoof any person's email. You can say, from whitehouse.gov. How much spam out there? A huge amount of traffic, email traffic are actually spam, 85, 90%, a huge amount. And of course, we don't see them. This morning, I checked my spam folder. I saw a whole bunch of spam, not a whole lot, because a lot of them are already blocked and removed through, filter, aggressive listing, and then it's doing a pretty good job. We all Virginia Tech all use the Gmail, and so all the emails in my spam folder, I don't care about them. Botnets has been used a lot, and then so you're looking at this. I don't know. Sometimes the video gets blocked. Like Ballbacks botnet has the spam capacity of 9 billion spam email per day, and so it's a huge amount of botnets that was recruited into those kind of campaign, and you can run them, and you can use others direct spamming and so on. SpamAssassin is a free open source detection mechanism. Is use filter, look at the header, look at the body, look at the content, certain keywords, and of course sometimes you generate false positives, but then most of the time you're actually pretty good. The filters are has to be evolving, and so this is a never-ending battle with spam, and just like security, we have said on the first day of class that this is just ongoing, constant arms race. You just, when you have certain detection, when you set up certain filter, they will do a different way, and then you just have to up your game. And by the way, interestingly, Verizon was under a class action lawsuit in like 15 years ago. I was trying to look up for the outcome and couldn't find any in my quick search, but some Verizon customers sue the company for being too aggressive in terms of filtering emails and blocking a lot of traffic from Europe, China, New Zealand, and so this is you just have to be careful. In how much do you want to block at ISP level, and how much you want to block, how much you would consider, and then sometimes you will wonder, okay, why do ISPs care about spamming? Maybe it's just let the users have the emails, and then they can figure it out. But then you realize that the ISP are carrying your traffic. They're like postman. If the postman carries a whole bag of junk mail, and you're gonna dump anyway, then maybe postman can dump it for you. And so this is really there's economic aspect of it, and of course all of this economics. Spammers also need to make money, and so this is why they send spam. So how to achieve email end-to-end confidentiality, and this we have been saying a lot. You do realize that it's by default this is not provided. Pretty good privacy PGP is something that I want to discuss very quickly. And of course you can use RSA, right? So you generate RSA, key pair, and then you let your friends know. And this is essentially the concept of what Phil Zimmerman did in early 1990s. 30 years ago. And he was under a lot of stress because at that time, when he released the open source version of PGP, and then that supports the Algamo encryption, DSA, RSA, and different range of encryption and digital signature. And he was targeted for a 3-year criminal investigation by the US government because at that time, believe it or not, cryptographic software was under export control and was considered as sensitive as nuclear weapons. And so it's dragged along lawsuit, and a lot of people worked for him pro bono. And the good news is that later on, there was a simple email sent out to his attorney saying that we're gonna just drop the case. No explanation and nothing, no apology. Don't expect government to apologize to you. But the idea of PGP is very intuitive. We talked about public key infrastructure, the CA and the root CA, second level, and so on. And it's a hierarchical structure. And here, so you have to trust the root CA. That's the organization, Verisong, Thought. And then you have to probably pay them a lot. What if you don't have that money and you don't trust them, right? So you can have this grassroots type of trust, and it's called web of trust. If I trust Alice, and if I trust Little Red Riding Hood, and trust the grandma and mother, and then we all trust each other, and then we can sign each other's public keys and endorse each other's keys. And that's the basic idea of PGP, and sort of give citizens the ability to encrypt messages so that no one except the end recipient will be able to take a look. And so today I read this great article he wrote and updated later on why I wrote PGP, and whatever you do will be insignificant, but it is very important that you do. And he cited again these quote, and so I encourage all of you to read it. And today is the election day, and just I think it just has a lot of deep meaning. So when now you look at this 30 years later, so that's so much for email security. Next, I want to talk about wireless network security. Wireless, we interact with every day, right? So you may not realize that you're actually using Wi-Fi access points. So the Wi-Fi is at the data link layer 2 in the 5-layer structure, and so is Ethernet. Ethernet, you may not personally use them because it's the wired local area network. If you have a desktop computer, you'll be able to find out the socket for the Ethernet connection. Both of them are for local area network. In MAC addressing is it's called a mandatory access control. It's a MAC address. Each computer has a MAC address already encoded and is approved by IEEE when it's being manufactured. In security, of course, is really important, and so here is a pull-down menu that shows different options for you to secure a Wi-Fi, and then sometimes you see this 802.11. That just the name of that the Wi-Fi protocol description specifications, and so it's actually cool. Extra cool if you say the name, like public key certificate. You don't say public key certificate, you say X.509. and so, but it's actually the same thing. Wi-Fi is of course it's local area network, and eventually if you want to do anything useful, you have to get out of it and go to the large internet and then get the content back. A lot of times that because of the network translation, network address translation net, and so your apartment may have like 10 devices, they only have one IP, and so there is this additional translation that's going on by the access point. And here a lot of people study for research ad hoc wireless network, like a mobile ad hoc wireless network, where it's, they form there's no centralized device that coordinates them. They like sort of relay information. And sometimes it could be useful in battlefield, in a remote area. There's no infrastructure. One of the example is called the one laptop per child, and this is in Nepal. It's an Asian country very close to a Himalaya region, the mountains, and so this is like what people say is $100 laptop, and you can have like the entire village have a satellite pole, and everybody just form ad hoc Wi-Fi ad hoc network to relay messages, and access point AP is very important. Many times that when we say encryption, it's between you and the access point. And so, for example, if you go to a coffee shop, you ask, okay, what is the Wi-Fi password, and that is regarding the security between you, the client, and the access point. And so don't think that, oh, okay, now I can send, my credit card in email. So if the email is not encrypted properly, then, anyone will be able to eavesdrop it, because they will also have the password to access the Wi-Fi access point, and then they're in the same network. And so as I said, that it's local, and so if you look at the 802.11 frame, you have not the access point AP's MAC address, your own MAC address, and then you also have the router's MAC address, because once you get out of this LAN, you will have to be able, the people will have to know, access point will have to know that where to send this frame. And so there's just a different way of addressing this. And for network, that's of course has nothing to do with security, just a network, how would you route frames at the data link layer. Security is important. The TJ Maxx data breach we mentioned before actually started because the person was doing war driving, which is just very odd name, but then it refers to looking for open Wi-Fi hotspots. And he found one when he was driving on Route 1 in Miami, Florida. And so because you may wonder, okay, so what? Well, if you have a store that has an open Wi-Fi, no passwords, or weak passwords, and then some of the transaction information or data management, logins, may be sent, like the manager was using the phone to log into certain websites, and that, maybe there's not a lot of, no strong end-to-end encryption, then you enable attackers to eavesdrop the traffic, and so it's not just it's not open Wi-Fi you're immediately doomed. Open Wi-Fi is not, but then if you have open Wi-Fi and then you have sensitive data sent over the open local area network, then you're gonna have problem. Most of our effort today will be explaining what is the word equivalent privacy in WEP wide fails. It's the first attempt. It started back in, I think, in the 90s, so a long time ago. It was designed a long time ago. It uses stream cipher. You recall stream cipher is different from block cipher. Block cipher is where you wait a little bit, you get a chunk of data, and then you encrypt them, and then you also have to use and then you encrypted this block using permutation, substitution, and then you also do block cipher chaining, right? Cipher block chaining, CBC. That means you wait until you got a whole bunch of other blocks, and then you chain them together. The one block's output goes into the other block, and then in the end, the penguin, recall that this little penguin will look nothing like a penguin, and it's just a whole bunch of blurry pixels. Stream cipher is different. Stream cipher is you give me one bit, I will encrypt one bit. You give me another bit, I will encrypt another bit. First is faster, right? So you don't have to wait. And the particular one that's called the Rivest Cipher was invented in the 80s. And then the assumption is very important is that the keys should never be reused. And then the key is very short, 40-bit long symmetric key. There's also an initialization vector which you send in the clear, and so it's just kind of like DES, but then it's a stream cipher with very short key. And so what you do is that you just generate a whole bunch. You use the initial key together with the IV, and then you generate a whole bunch of keys, and a whole bunch of keys are used to encrypt information for this frame. And then if you have another frame, you get another key, and you generate you generate another whole bunch of keys to do the encryption. And the encryption is XOR, which is of course very simple, and there's also cyclic redundancy check. And the problem with this, a characteristic, it's not necessarily bad if you do not reuse key, but then one characteristic of stream cipher is that the ciphertext would, if you XOR them together, you're gonna have, and then assuming that they have the same key, then you will get, because of the properties of XOR, you will get the XORs of the plain text. Okay, and so you kind of, by observing ciphertext, you learn something about the plain text, which is never good. You know, remember when we talk about information security, you know, theoretical security, Claude Shannon, information theory, we said that the best way to secure message is that the ciphertext has nothing to do with the plain text. Now you see that there's some correlation. Correlation is never good. For example, if you see that ciphertext is the same, you know, A and B are the same, then you know plain text is the same. If they come very close, must be under the same key, or you know, you just have some knowledge of that the key may be the same, and so it's never good. And then even if the plain text is not the same, you can use some statistical analysis and just to get additional knowledge. And so one of the fundamental issues is that the key is too short. The key is too short, and therefore it gets wrapped around very quickly. And superficially, you see, okay, it's the key is 40 bits, so it's pretty big, right? Pretty big, and the initial vector is pretty big. But then you realize that we talked about this birthday paradox. Is that it's even though it looked really big, the number 60 million, blah blah, the collision will happen pretty quickly. And we said that you can estimate the collision of the number of data points you have that give you collision greater than 0.5. Probability is just do square root of the entire universe. In this case, it's just 2 to the 12 is 4096 initial vectors, and so that's pretty fast. If you are doing wireless, you know, transmission, you know, one frame for one key, and pretty quickly you're gonna have wraparound, and that's what the researchers demonstrated back in 2007. You can end up, you know, just a break WEP in a few minutes. Okay, and so it just really insecure, and of course most of the time that you know, when people, when WEP was actually used, it would, you know, you didn't see a lot of reports saying someone's WEP got hacked for real. But then it is pretty vulnerable. And CRC is also having this weird CRC also, because of how CRC is structured, it has this sort of properties, so you can infer additional information, and this enable attackers to manipulate the message. And we said that if you are considering a malicious threat model, malicious threat model, intentional attack, not just a bit flipping, transmission error, very benign, that kind of issues, you really shouldn't use CRC. You should use keyed hash, digital signature scheme, public key, symmetric key. CRC is for inadvertent errors, not for malicious threat models. Right, so what should you use for message integrity? Not CRC, you should use a keyed hash, assuming both parties have shared a key, or digital signature scheme. And in the Wi-Fi scenario, most of the time it's a keyed hash. It's fast and easier to set up. Because once you have shared keys between you and the access point, you'll be able to do this. So summary of weaknesses is not just one weaknesses, it's multiple weaknesses. Probably they shouldn't use stream cipher. Even for stream cipher, longer key should be used. And also the original implementation choose the initial vectors sequentially, which is make things very predictable. And so if the keys are the same, IVs is predictable, then just you don't have a lot of entropy when you do the encryption, and so WEP, that was the most important slide of this class. If you graduate from Virginia Tech and then people ask, can we still use WEP? You should definitely say no. Okay, it's a broken squarely, and just don't even try. And so you may think that, oh, okay, well, I mean, we talked about TLS, and then we said DNS is kind of like TLS, IPsec is kind of like TLS. Maybe we can just do for a local area network, and then TLS like kind of protocol to achieve confidentiality, integrity, authenticity, and then be done with. The answer is yes and no. Yes, of course, you can have a powerful access point. A lot of enterprise systems, and they have the access point is essentially authentication server, have the certificate, and then be able to do mutual authentication. Certificate very much like TLS. It's certificate verification, derive similar keys, and then do that. But the answer is also no. In some scenarios, especially personal scenarios that you may not have the users may not have the ability to install certificates and then to be able to do this kind of verification, installation of certificates, and so there's some deployment constraints in that not necessarily that you have to use a big gun for the local area network. And so, but then the concept, you're definitely right, TLS type of concept, right? So you want to make sure that you are talking to the right access point using just a stronger form of cryptographic primitives. So improvement has two levels. IEEE offered the first level of improvement is WPA, with just longer keys, and so that it's just to take longer time to have collision. And then there's also, and so longer keys, how long is this? From 40 bits to 128 bit, and the initial vector also double the size, making it harder to predict. And RC4, interestingly, is still used in WPA because of, not because it's good enough, it's because of backward compatibility. The routers, the machines, the appliances it turns out it's hard coded, implemented just for speeding up things. And so in order to utilize existing hardwares, it's the WPA has to use the RC4. But it does introduce this is a key integrity protocol which allow sequence number to be generated for each frame, and the sequence number is not predictable, and so therefore prevents replay attack. And then a key derivation function to generate per frame keys. So there are better and longer keys and better key management. But then the actual encryption is still stream cipher, use RC4. Luckily, the CRC is replaced with message integrity checking, some sort of a keyed hash. And so this is a high level diagram showing the four phases, and you see that it's very similar to the TLS phases. You have first the client, it could be our phone, a laptop, and would negotiate with the access point, making sure they're talking to the same algorithm, same version, and then they mutually authenticate. We'll talk a little bit about this. So how do they do it? And then once they figure out who each person is, and then they derive a shared key, a shared master key, which can then be used to derive additional encryption key and a signing key, and the integrity key, very similar to TLS. And then data transmission use the derived keys. And then for mutual authentication, WPA does not have specific, WPA is a framework. It's offered different ways for the actual implementations to authenticate client and the server. And so many different flavors for the developers to implement what is called Extensible Authentication Protocol, EAP. And you can use password, you can use certificate, and so it's flexible. For example, one of the key, the mutual authentication, is use the Diffie-Hellman key exchange. And so you set up, you say, client hello, and recall that we have the key exchange, the raise the base G to the power of the secret, and so that is the Diffie-Hellman key exchange. And so you can have different options, and so I want to so yes, okay, all right. So why is the public key infrastructure optional? Why are we not talking about, oh, it's extremely important to make sure you use the right public key certificate, and to checking the CA? Why there seem to be like different flavors of it for the wide area network. On the internet, we said that it's just absolutely, there's no flexibility. You just have to use certificate, public key certificate, get signed by the CA, and there's no workaround there, that actually use that. Why for LAN, there's so many options, and seems to be some are kind of not that rigorous. Why is that acceptable? Well, for local area network, first of all, that it's you don't go very far, right? So you know there's a router. You have access point. Your router you bought online, or there's, and it's there, okay? And then for you don't even get to see Amazon's router. And so there are not many servers on a local area network. And so it's relatively simple. It's actually a lot simple. You don't go onto the internet. There's not intermediate routers in between. And so it's more direct. It's a more direct. And of course, you also don't reveal your credit card to your access point, right? So they shouldn't. You don't tell your social security numbers to your access point. So the type of information that you share with AP is also less sensitive. And it's a closer, and the information, because it's at lower level of the network stack, the information you share is also less sensitive. And that certainly means that you do have to, if you send your social security number at the Starbucks open wireless network, you do have to do end-to-end encryption. You cannot just send it as an unencrypted like UDP traffic. That would be very unwise. And so but then local area network, we emphasize on usability, convenience, right? So you don't want to go to a Wi-Fi Starbucks and then start to install all kinds of certificates and of something just for mutual authentication, so you want to things to be simple. So a lot of times the password is okay. And WPA 2 is the real deal. In WPA 1 is mitigation, because we have to be backward compatible. And now with if you buy newer hardware, it actually support AES, the right algorithm is no longer stream cipher, it's block cipher, and you support different much longer keys, and authentication, EAP still continues, but it's just a brand new algorithm, WPA2. So WPA2, if you're able to use it, and do choose it. And dictionary attack are still possible, and so it's not like it's bulletproof. Nothing is bulletproof, right? So like, for example, RSA, people can still do like brute force attack to guess RSA keys. So you cannot stop people from doing it. There are still ways people may try, but then when you have longer keys, it's just gonna take longer, and probably by the time they break your key, you already left at Starbucks, and so and it's just may not something that you don't worry. It's not that risky. Before we end today, I want to explain what a cross-site request forgery is. We said we had, when we gave overview, we mentioned this example. This is very scary example. The other day I was watching one of our YouTube comments. My YouTube lecture, one person said, "Internet is so scary, I'm so afraid." No, don't be afraid. Cross-site request forgery has a token that's embedded in most of the Java Spring enterprise implementations, and so there are a lot of default preventions. But what happened is that the user has already ongoing connections with bank.com, which is a legitimate server and has this cookie, session ID, whatever credential stored. But then accidentally visit a website of an attacker, which trigger the submission of a form on behalf of the victim to the bank. And notice the form is not an actual legitimate form coming from like Bank of America's website. Is coming from the attacker, and then but then it's sometimes it could be invisible, or it's just, like hidden, and nevertheless it's ask the bank to transfer a certain fund to the attacker's account. And ordinarily this would not work because you don't have the victim logging into the bank. But in this scenario, we said that the victim already has a credential in the browser, and the browser would look at the request to bank and see, hey, wait a minute, I already have the credential. I don't have to bother the user to log in again. I just attach the session ID together with the form, and then transaction done. And so so this is very bad. And then sometimes it's called a confused deputy problem, because who is the confused deputy? The browser, the victim's browser is a confused deputy because it's not a real request to the bank, and the browser couldn't tell. But browser only sees a request going to the bank, and therefore automatically attach the store to the cache the credential. And this would happen a lot, because a lot of the credentials are long-lasting, long-lived, and last for like weeks, and so you don't have to log in again. And so next time, a few days later, when you do any transaction, it's still working. So the cache, you may think, okay, the cache, the credential is one issue, is the root cause. It's part of the problem, but not all. And as we will see, that it's short-lived credentials. That's definitely one of the solution. But also, can someone tell the form coming from the real server or the fake attacker's website? That's another issue. It's worth mentioning that because of same origin policy, the malicious site cannot read your bank information, but then can still submit requests. And so the same origin policy does not prevent cross-site requests of forgery. A couple more examples. For example, here you have Alice already had a valid session, and then visit a malicious website. Malicious website may send a password change request to her service, and so this is could be a hidden form you don't see, but then when you visit a certain website, it just gets automatically loaded. Then at the end of the transmission, the Alice password gets changed. And so this, as a matter of fact, is the beginning of the first time when researchers notice this attack. Someone's passwords gets reset. I think the Gmail passwords gets reset. And of course, that was like 13 years ago. And then people realize, oh, this is not good. Another example is where you have a valid session, and then the attacker you just have to load this particular URL. And then a lot of times that we said that a post is really a get. Now you want to submit form, you can just use a get with this field value attached to the URL, and so attacker only need to have the victim load this URL, and then the URL you could embed in an email click, phishing email, and so on. They can also be loaded automatically, and in this case is if you embed this link and then Alice accidentally click this link, the link on the outside it says view my picture, but then it's really, the link is a URL request. It's really a submission of a form. This is slide. Another example is even harder to detect. You have a source. If you program in HTML, you know that in the image source, so you a lot of times it just gets loaded automatically, right? So you load the page, you grab that image, and then this is tiny image, width 1, height 1. Okay, so this it's almost invisible. But then it's not really an image, it's a URL. And then when that URL gets executed, it's becoming a form that's it's a form with submission to the server. And so it's very dangerous, very hidden, it's very, because of the long-lasting credentials, and this is gonna be very popular, and it's relatively easy to launch. And so this is a time to talk about solutions. And the good thing to know is that there's multiple ways to prevent cross-site request forgery. And we said that same origin policy doesn't work. Cookies, session IDs, and then just there are ways that restricting certain type of requests, and not all of them are not very effective. And what really should do is you certainly short-live the credentials, delete cookies after transactions. And there's also referral field that HTTP header has, which means if you get redirected to a certain page, the original site is the referrer. And so if you visit if you send a certain form from the attacker site, that request should have attacker's domain in that referral header. And then the server, if you check the referral header, will be able to detect and see this is not directly coming from us, this request. And so sometimes this can be forged, so referral is not a good and not a rigorous way of prevention. The best way is to have a token embedded in the form, so that only the original server can generate, and attacker would not be able to guess it, and therefore would not be able to put up a fake form or put up a fake request, because all the requests that are legitimate should be coming from the authenticated the real server. And so this is called anti-cross-site request forgery token. Sometimes people call it synchronization token. I feel like that name is not very intuitive, but anti-cross-site request forgery token, it is the canonical name. And it looks like something like this. It's just a random looking string that you cannot forge, you cannot guess, cannot replace, use only once. But on the other hand, it's easy for the legitimate server to verify it. When you receive a bank transaction request, that request should have a token embedded as part of the request value, the field. And then you just double check to make sure this is authenticate. If it's not, then that means this request could be coming from attacker's website, and then the submit or because of confused browser. So the concept is very simple. Let's explain it a little bit more. So you have the typical procedure is you send a request to say, hi server, I want to log in, transaction, transfer, bank balance, and then you get a form. This form, you don't see it, but there is an embedded field called anti-cross-site request forgery token. And then after you submit the form, the token gets submitted back. The server will check. The easiest way to check it is key to hash, right? So we talked a little bit about, so how do you make sure that this is authenticate? And if your key is secure, then only you can generate it. Very much like the SYN cookie. We talked about, preventing SYN flood attack, right? So the server will be able to embed some secret and then be able to verify this is indeed the server generated secret. So think a little bit how to do this and just, use keyed hash. And so under the attack, what happened is that when the form, the attacker still be able to submit the form, the post request, get request, but then that request will have a missing token or have a wrong token that doesn't check out, and therefore the transaction will not be approved, will be rejected. And this is the last slide. So that was good news, right? So we have multiple ways to prevent this dangerous attack, very subtle, very dangerous, and seem to be easy to launch. The bad news is that even for cybersecurity, it never ends. The bad news is that a lot of times that developers don't know how to enable this token, and they have no idea why it is enabled by default. And so this is one of my work with my colleagues, and we look at Stack Overflow forum where developers, they ask questions, and one of the answer is to disable the token. And it turns out that is the most popular answer, and people are like celebrating. Well, this is just a great solution. Just disable the token. So please now you have taken the security course. You know that this is something that is so easy for attackers to pull off. So don't disable it. Just figure it out. And in the meantime, if you work on developing security solutions, make sure that the documentation, make it easier for developers to learn. Imagine you're like 60-year-old developer, you're sitting, and you never heard of this, and now there's new technology and you have to learn. It is frustrating. So do if you're in the technology development, and make things easier for developers. So I think that's it for today. We'll be able to we have one programming assignment coming out soon, and there's also one written homework assignment is going to be just a complete like complete versus incomplete. So that will also coming out soon, and in the meantime, do work on your project, because project update assignment will also come out soon. You just need to send a 1-paragraph update, but still you have to continue working on the project. In general, I want to reduce the overlapping of assignments, but then this is usually every semester. This is a time where you do have to have a little bit of multitasking ability going on. Other than that, this is the end of the lecture. We'll resume on Thursday. Thank you.